to look at for like forever. And it's come up in the context recently of some physics project work, and that's caused me at least to figure out that there are, in a sense, simpler ways to handle some of the key questions in logic programming. Basic issue is, given a set of rules, how do you collect them together to get from one place to another? And let's take a look here. Now, this isn't adequate. I mean, hold on. Development. Okay. What is the, I don't know what exactly is different between Mano's version of this. And so I had a version, then we had a version that's based on multi-way systems. Then we had various other versions. Find string replace path. So well, let's take a look at what these things actually do. Let's look at find string replace path to begin with. Right, so the idea is that we are given a collection of rules, like here, let's just say, right, this is a reasonable example. Okay. Oh, yeah. Okay, so people understand what this is doing, yes? This is saying, what's a way of putting together those rules to get from A to B, right? Yes? Understand? No? Don't?
Okay.
Okay. But now, you know, back in the day, right, people were obsessed. I mean, we're now talking 25 years ago or more. People were obsessed with Prolog and its way of doing, sort of goal-based programming, right? And now we have a machine learning function, don't we? That is doing something a little bit like this. Let me just see. This is, yes. So to what extent does active, okay, if we say active prediction, right, active prediction, let's see, how does this work? Applies the function to successively generate configurations starting from one of these things. So to what extent is this the same idea? Do we understand that? Do we know that? Anybody got an opinion?
I don't. It's the first time I'm seeing these functions.
Okay.
It doesn't seem that that function is applied multiple times.
Is that right? I mean, it is, in other words, is it? I see. You think all right, so it may not be related. Let me just save this away in some appropriate place. Let's see if we have stuff from like millions of years ago. Oh wow, we have a thing called logic programming here. 01. Let's make a let's just take a look at that thing in a minute. just for the hell of it, let's find out what we wrote probably many years ago here about the same topic. Hold on 1 second. Oh yeah, 5 years ago. Here, let me put it in that folder. Okay, this was written in 2015. Oh my gosh, we had the exact same function. We had the exact same function. Well, that's a good sign. Honestly, that's a pretty good sign.
Yep.
Wow, we just didn't implement it. Okay, so then we had this idea. Okay, a find goal sequence where there are scores. I mean, this first one is okay. So this relates to what you can do in kind of in the multi-way games business. But I don't know how the scores really relate here. So I'm actually very pleased that the function is exactly the same function. I am at least deterministic, even if nothing else is here. Ethan is commenting that active prediction and active classification are both impossible to use in real machine learning problems and need rewrites. Well, it'd be interesting to get input about why. They have not been popular functions, that is for sure. And I don't really understand what. Okay, so hold on a second. Let's just what was I looking at? I was looking for the multi-way games business, which I think will be helpful here. Let's see. Hold on. Just a second, I need to find this. Oh dear, where did I put it? Oh, here we go. Well, I don't know which version of this I should look at, but let's try randomly a particular one. Okay, so this is looking at, okay, so this is simplified tic-tac-toe. Okay, and so the find replace path would be something that says, can you get to the winning state? And the scoring is a question of knowing whether you're getting warmer, so to speak. It's a hint, right? It's not, well, I mean, I guess that this is related to, okay, so hold on a second. So the issues here are, can use, okay, so case one, there is a definitive endpoint. Okay, or maybe, or possibly a pattern for the endpoint. Am I making sense? That is that there could be several different possible endpoints, but they all have a certain pattern form. And then case two, which segues into more of a machine learning story, one just wants to find the highest score endpoint, right? So that's the case where you've got these rules and you've got a scoring function and you're asking, how do I apply these rules to get to the highest? And that's almost a traditional, optimization machine learning type problem. Am I making sense?
Also reminds me of the problem in group theory of given generators, find the decomposition of a given element in generators.
Yes, yes, that's true. So given, I mean, but that's okay. So let's list some of the things that use cases. Okay, so I agree that given a word / path or path in a group, decompose it into generators. Now, is that the same thing? Because what you're asking for there, okay, so that's a little different because in this case, yeah, I guess you can always do that by saying there's a rule. Let's look at that for a second. So the rule, you're okay. In this case, you're in this case, it's like the strings. You're adding to the strings here. Yeah, it's really very much like this. This is like a semigroups. That's like a monoid, right? The string case,
right, is
like a monoid version. Now, Jonathan, for example, has multi-way group, which presumably essentially does this, right?
Yeah.
So my question, there's a question here of what is the universe of things? Okay, so let's take a look at what we did in 2015 of our, different use cases here. Okay, so we've got,
on the group theory front, if you'll recall, this is the thing that I think you and I had a disagreement about in the design of multi-way group.
Yes. Well, you have this.
I was arguing that we should allow a rule where you can basically multiply at arbitrary positions, because that's effectively doing this, right? It allows you to solve a generalized word problem in which you're doing decomposition into generators. Whereas if you only allow multiplication on sort of one side, then unless you assume commutativity or some other nice sort of algebraic feature, you can't do the same thing.
That was not my recollection of the difference. I thought you had this novelty generator where you have a rule that says nothing goes to, and then nothing goes to a generator.
But those are exactly the same, right? Because if you say no, okay, so if you treat the thing as a monoid, right? Or if you think of the thing as a string with a monoid structure where the nothing is your identity, right?
Yes.
Then nothing goes to whatever is exactly the rule that lets you multiply by a generator at an arbitrary position.
Okay, hold on. You're claiming that the thing that says essentially nothing goes to what? Not nothing goes to a generator. Nothing goes to a generator multiplied by its inverse, for sure.
No, but that's simply an equation, right? I mean, that's there in the axioms of group theory.
Yes.
Right. What I'm saying is that when you want to do the decomposition into generators, so what I was doing was tagging. So there are several different types of rewrites in multi-way group, right? There are rewrites that are simply axiomatic, like that one there would be an axiomatic rewrite.
Yeah.
There are rewrites that are as a consequence of the relations, and then there are rewrites that are a consequence of you multiplying by a generator at an arbitrary location.
I see. So what you're saying, okay.
That's a case that you care about when you want to do a decomposition of a word into generators.
Right. So what you're saying is so in multi-way group, there are basically meaning neutral transformations. Then there are probing transformations that try to figure out whether you can construct a word that gets you to that particular place.
Exactly, and so your design for it, which is supported with the option append only. If you set append only to be true, then you get your design, which is where you only have the meaning neutral transformations and multiply on the right. But then there's the default is the full form, where you can multiply in arbitrary positions, which has that kind of novelty.
But wait a minute, multiplying in arbitrary positions kind of violates the sort of the. I mean, that's okay. Then Okay, what we're saying is there's the difference between it's the old difference between theorem proving and setting up equalities, so to speak. But it isn't really an equality in this case. It's a yeah. Okay, well I understand. At least I understand that better. But so in a typical case, okay. So let's again talk about use cases here. One meta use case. Okay, here. There's sort of another case here, maybe. One wants to find a proof. One wants to find an equivalence proof. So in other words, that's a case where in that case, every step is somehow considered equivalent to every previous one. Right, so in other words, in this case, it's like one's reaching out from point A to point B, right? That's a definitive, you're going, so that's a find replace path. I mean, I don't know whether replace is right. The general case of this would be find, it's a general, let's see, find operation path or something. Well, actually, we could call it find function path. And find function path is, you've got, actually, that's a different case, right? I mean, okay, instead of replacements at all, right? Yes, there's a different thing here. So, okay, so I'm going to claim there's find replace path, there's find string replace path, and there's find function path. Okay, find function path would be FGH XY, I think.
So find replace path and find string replace path would just be special cases of find function path for replace.
That's correct, but which probably can be done much more efficiently in various ways.
Right.
Steven, you were saying when you find an equivalence proof that each step has to be reversible, but I don't think it has to be that strict. I mean, the forward path and backward path might be completely different. You still get equivalence.
Fair point. Fair point. Though the okay,
which will in general be the case if you have sort of generated variables on one side of an equation.
Right.
Can I make a meta comment here? I mean, there are a bunch of other things that one can do with logic programming, and like, for example, in general, one is interested in knowing if something is a theorem. So if something can be achieved with a set of replacement rules, or even enumerating all possible things. And another important case, I think, is unification. So figuring out when you're matching a replacement, what gets unified with what.
Right. Actually, the point. Okay, so this. Okay, so there's a case 2A here. Find an endpoint that satisfies a criterion, e.g., tic-tac-toe.
Yeah, or for example, the Einstein problems. You want to know, who lives where, given
what?
The Einstein problem. You know that the person who lives in the yellow house is next to blah blah blah. Where does John live? That kind of constraint solving. That's also often done with
right,
or Sudoku, whatever. You want to know what number goes where.
Right. So this is, well, you need to know the path, in other words.
I mean, the path is not that relevant there. And in many cases, there might be multiple solutions. It's not the case.
Of course. And I mean, in find replace path, find string replace path, we have something. If we look here, at what's this? Oh, it's the definition. I've never heard of Einstein's riddle before. Wow, I wonder whether old Albert actually wrote this himself.
It's weird because I thought you taught me the name Einstein problem when we were talking about Mini-Cameron, but maybe it was somebody else.
I don't think so. I think it was somebody else because I don't think I ever knew this. Okay, in any case, what we've done in find string replace path, we do have the ability to find like all paths and the multi-way fragment that describes. So this is something for discrete paths that makes decent sense. But I think we're always dealing with discrete paths. I think that's the only case of relevance here.
Yeah, but I mean, you have to know what the solution is, right?
Well, no, but I mean, we're saying that in all of these cases, you want an endpoint satisfies a criterion, you want the highest score, et cetera, et cetera, et cetera. Now, you were talking about unification, so let's talk about that.
No, Carlo's making the point that an endpoint that satisfies a criterion will in general not be a literal string. It will be some equivalence class of strings, which we don't have the ability to specify either here or in the theorem proving framework. Right, it's a different.
Okay. Well, okay. So let's. Okay. So hold on a second. So then,
it's like so the theorem prover can solve logic puzzles if you tell it the solution, right? So it can check if you set up an Einstein riddle, it will tell you that the solution is correct if you give it one, but it can't generate a solution because that would require being.
And also, like the Einstein riddle is usually expressed in terms of constraints, not in terms of replacement rules. The replacement rules are kind of trivial for the Einstein thing. And it's the same with Sudoku.
Okay, well, let's talk about how that looks, what that looks like. Okay, so find function path specifies a bunch of moves that are legal moves to make. So an alternative would be yet a different case here, which is some kind of find constraint path, where what you're doing is you're saying you can make, so where you both have, okay, so there, maybe it's folded in with this, you have a generator of motions, and you have a constraint that it must satisfy. So in other words, you're not saying explicitly what, and I think that's similar to what active predict and so on tries to do, and maybe doesn't get to do a good job. Is that right? I mean, this is the, so in this case, you have a local constraint, yes or no? Is that right? I mean, that constraint is intended to be a constraint on each application of the motion. Is that correct?
Well, if you think about Sudoku, it's usually on the end result, like whether or not it's a valid.
Okay, but that's a different case. That's a case we've already talked about here, which is the endpoint satisfies a criterion.
Yeah, but not just the endpoint. Every time you add a number, the board has to stay valid.
Then that's what this is.
Yeah, that's what I was
saying.
saying.
You have a constraint it must satisfy at every step.
Yeah.
Right? Okay, so Jonathan was showing here a okay, let's understand your comment about unification. Okay, so what should I look at here? If I look at
there was something I sent to you in 2018, an email titled Mini-Cameron, which contains a notebook that should run.
I'll find it. It's only 2 years ago.
I didn't work on it 2 years ago. It was longer ago than that, but I sent it to you.
Do you think it's one word,
Mini-Cameron? In 2018, February 2018, titled Mini-Cameron.
Well, if you have it, then
I'll say.
Here we go. From Carlo, here we go.
Yeah, Carlo,
Mini-Cameron tutorial equivalents.
I remember you showing me the Mini-Cameron implementation you had back in at the 2017 summer school.
Okay, all right. So this is your mini cannon thing. So let's take a look at this.
So
Let me
one
save
thing that
this.
it does in terms of unification, for example, is that if you give it an under constraint Sudoku, it will still find solution and say, you know, this is the set of solutions.
Hold on. Okay, so let's look at this. Let me ask this question in terms of just practicality of implementing these things. Does, I mean, did you integrate mini cannon in some way with the system?
No, I mean, the code that is there is like about 150 lines of code, but it's not efficient at all. Like if I were to go back and write this again, I would probably, you know, now Z3 from Microsoft is MIT licensed. So maybe it's something that we should look into because it would be much, much faster.
Okay, can somebody walk me through what the relationship between our equational prover and Z3 and so on is? Z3 is a constraint programming system, yes?
It also has theorem proving, I don't know of what flavor, and a SAT solver.
Okay, we already have a SAT solver. We already have a good SAT solver. That's not the problem we're trying to solve here. I mean, does this need SAT solving somewhere in the middle of it?
No, I mean, this is something that.
Okay, so then let's just understand. Okay, so the main point here is we want to get, you know, convenient design. So to me, there are several different things you want to get out of this. You might want to just say, okay, so in other words, in these use cases here, right? So meta use cases, you know, which of a class of endpoints can I actually reach? Is there a path? Maybe how long is the path? Maybe, I don't know how that's maybe less important. That's a meta question, really. Is there a path? What is the path? What is the, e.g., shortest path? Perhaps variant is, what is the path that optimizes such and such a criterion? Am I making sense? In other words, that if there are multiple paths to choose from, length might not be us. So really what we want is a criterion for choosing paths, right? Criterion for choosing between paths. And that might be a local criterion saying, don't step on the hot lava, or try not to if you can avoid it. And it might be a global constraint that says, I want the shortest overall path. Does that make sense? And let's just look for a second back at our.
Can I say something before we move on? Before you put mini cannon behind.
No, I'm going to come to mini cannon. I wanted to talk specifically about mini cannon. Just a second. I just want to look at our next states and scores. Okay. So these are examples that we had from before of hold on, I just have to organize my okay, so these are from before, some use cases here. Chemical synthesis, which we've now discussed at more length. We've got a variety of game solving, which is mostly, I would say, I mean, and then, and then the various kinds of planning problems. Yeah, Brian is asking about chess problems. Yeah, I mean, this is exactly that's the type of problem that this should be able to do. And that's like the 8 queens case is a common test case. Can we already do 8 queens with presumably, can the theorem prover do that?
Yeah, but like I said, I mean, it can check solutions that already exist. But basically the key thing that Z3 and Minicanron and these other kinds of logic programming languages do that our theorem prover doesn't do is have the ability to basically generate proofs of theorems where parts of the theorem are underspecified. Right.
Okay. All right. Generating paths/proofs where the endpoint is not definite. Is that what you're saying?
Right. Okay, so this is a general difference between theorem provers, theorem verifiers and logic programming languages. So like Minicanron, there's this thing called alpha lean TAP, which is a sort of nominal logic proving environment in Minicanron. And so you can give it a theorem and it will give you a proof. So it's in that sense, it's a regular theorem prover. But on the other hand, if you give it a proof, it will give you the associated theorem. So you can use it to check proofs. But also it can do a hybrid where if you give it sort of part of a proof and part of a theorem, it can fill in missing pieces. So you can use it to kind of exploration.
Wait a minute. Given a proof, it will give you the theorem. Why isn't the theorem just beginning of proof equals end of proof?
It is if the proof is correct.
There's, I mean, the stuff that Minicanron is, I think, where it's very different from our theorem prover is that you can do things like, for example, you can ask it to generate quines, for example.
Generate what?
Quines.
Yeah.
So you can I mean, at least in its original implementation in Scheme, it knows about the Scheme syntax, at least part of it. And so it can generate programs in Scheme that satisfy a certain
big frugal double. I mean, yes, you can generate combinator expressions too, no doubt. With any of these things, we've got a multi-way combinator system too. The question of what the syntax of what it's generating is, it doesn't seem terribly important.
No, but there is a more fundamental point, right? Which is that this function, this sort of super function in Minicanron, evallo, which lets you relate, an expression to what value it evaluates to. The fact that one or both sides of an evallo expression can be underspecified means it is strictly stronger than a theorem prover, right?
Okay, all right. So let's where the end points are not definite. So what you're saying is I'm trying to reduce this to like functions here. So I mean, what you're saying is find function path where find.
No, I'm saying something much stronger than that.
No, you're saying that you've got an initial condition that satisfies, you've got basically, I don't know what the right name for it, but let's say find constraint path. No. And then the initial condition is specified by init crit and final crit, if I'm understanding correctly. Those are criteria as opposed to being a definite thing. Is that right or is that not right?
Well, no, as I say, I'm saying something much stronger than that. So what Minicanron can do is it's not just finding paths. It can deal with the hybrid case of you have a partially specified path and a partially specified sort of a set of criteria, and it will fill in the blanks in both.
And the other thing is that the rule.
Okay, well that's magic, but how would we represent it?
No, yeah, wait. I think that the first problem is to represent the rules in a similar way to how Minicanron does.
Okay, you know what, guys, look. We have a nice general symbolic way of representing things. The goal is not to, descend into some thing which is hardly, a consumer-used, mechanism. What we want to do is not this type of thing where we're setting up some complicated state.
No, right? But in the end, I mean, those I was explaining those as, but if you look, those are internal tools. If you look at two goals, what minicannon, the way you express rules in minicannon is strictly two-way, and it's basically you can unify replacement rules in both directions. That's the big difference. So if you look at the one just above, just two goals, it's an equation.
Where are we looking here?
Just after set, blah blah blah.
Oh, two goals. Here we go. Okay.
Yeah. So you're saying I have a sequence of integers on the left, and on the right I have just a blank with a pattern test. What are the ways in which I can choose x and y to satisfy this equation? And then it just goes and generates x and y's. So it's not
okay. I understand. So that's like find instance or something, right?
Yeah.
So there's a find instance case.
Right. So Stephen, at least in the context of the theorem proving stuff, the most direct translation of the kind of something like an eval-o operation in WL would be to have the ability to have a partially specified proof object, and then a function that then fills in the details. So where either the axioms or the theorem or the proof can be underspecified.
Yes, I understand. I mean, my concern is how on earth to specify that, whether it's with patterns or whether it's with something more general.
So I would say patterns or an explicit quantification would be the obvious way to do it. Or, I mean, from a logic standpoint.
And also I think rather than, I mean, it's actually a little bit less than patterns, because our patterns are too general to be able to deal with. Like,
no, our patterns have undecidability, which,
yes.
you know, so, but that's life.
A subset of the pattern language.
But you see, but Carlo, the problem with this is, and this is what killed Prolog as a practical thing, is that, you know, it's very easy to specify things that are extremely hard to do. So the challenge for us is to figure out ways to specify useful things that are still doable. And that's why, for example, things like find string replace path or find replace path is a nice doable thing, right? It's a nice thing where people can understand what the point is and you can actually do it.
Yeah.
Now, I mean, as soon as you descend into you've got arbitrary programming on both sides, no, you can't do it. And you have to go ahead anyway. Okay.
Yeah, you can't do it. And there's another thing that makes it, I mean, the way I restricted the problem, and it was hard enough this way, is, I mean, the main hurdle I had to, compared to scheme, is the fact that expressions in the Wolfram language can have, and patterns can have arbitrary length sequences, while in scheme, everything is a binary tree.
Okay.
And so when you're matching,
fine. I mean, that seems like okay, but you also talked about unification, which is not completely dissimilar to this issue here. I mean, I'm trying to.
No, that's unification. Yeah, I mean that particular thing doesn't have a unification that solves it. But if you look at the one, there's one below which is just EQ check QY. That thing is just it has one free variable which is Q, and it's trying to find the solution Q equal Y, and the only solution it can find is a blank. That is, since also Y is not specified, it finds a pattern. And the one below, it finds two solutions, it finds an alternative.
Okay, but so in our world, what this is doing is solving a pattern equation. Now, I mean, we've worked on, so there was a project, long-running project done by a student person, which was a string equation solver, okay, which was quite difficult, used some quite fancy algorithms. I'm not sure it's even now been put even in the function repository, because it had, you know, there were only specific string patterns. Okay, so this is also, I just want to make a note, this is also related to, this thing is related to, whoops, this thing is related to string solve. But so that's a, you know, honestly, this is a different problem, I think, from these path-related problems. There's a whole class of problems that are, you apply this function, this function, this function, you're trying to get to this place, right? And I'm not quite understanding. And then there's something where you say, given these two patterns, what is their, what is their overlap, basically?
Yeah.
Right, and that to me is a slightly different, that would be something like pattern solve.
So I should mention that at least in the case of the kinds of patterns that are supported by multi-way system, we have code for computing MGUs implicitly in canonical branch pairs. And
what's an NGU?
Most general unifiers. Which
is what you're MGU. Sorry, I misheard. Okay. So then.
Because if you remember the way that canonical branch pairs works, basically is you give it a bunch of string rules or a bunch of multi-way rules, and it looks for it finds the MGU of the left-hand sides, and then applies all possible combinations of rules to those to the unifiers.
I do remember that. Yes, yeah. I do remember that. So hold on. So how would we make that into a generally usable function? And by the way, these things are also related. Also related to the stuff, the Sparkle stuff, isn't it? Where you're trying to find,
right.
I mean,
you're trying to find paths.
They are related to Sparkle, and I think that there is, on the other hand, there is like, I was telling this to Jose earlier, that there might also be an application to things like dataset. That is, you get data in a shape and you want to normalize it to something that a function can eat.
Oh yeah, absolutely.
Or you want to normalize it in a way that fits into, these normal forms that databases eat, because that's what Sparkle is doing, basically. It's denormalizing, actually. But
well, or alternatively, you have a form of visualization that's a histogram, and you've got this data. How can you get it into that form?
Yeah. Yeah, right. And that's the original reason why I started studying Mini-Cameron.
No, I understand.
I was working on alpha.
Right, I remember. But so what we've got to do here, the design challenge here is to turn this into probably, I'm guessing on the order of 4 functions that are, that do the things you want to do. I mean, personally, I think pattern unification is not as practically important as some of these pathfinding things. I mean, in other words, the thing you want out from, let's imagine that we say find function path, okay? And okay, so let's imagine that find function path is okay. So this is a good example actually. Is given all kinds of things that say transpose of blah comma blank blank whatever, right? And it's also given reverse, and it's also given, I don't know what, array flatten, a blah with blanks. You see what I'm saying? Okay, so now the question is, and you're given some data 1, and you're given a pattern for data 2, either a pattern or a criterion for data 2. Right? And you're asked, so then the result you might want to get here is a path that says transpose on axis 2, drop, blah, blah, blah. You get what I'm saying? To get from data 1 to something that satisfies the criterion or matches that pattern. Does that make sense to people?
Yep.
I mean, that seems to me to be a practical thing that we might want. And let's compare this, to simplify. Okay, so full simplify is doing something very much like that, except that it has, it has a cost goal. It has a cost function, right? Now, I mean, I don't know whether, maybe even this technology could be used by full simplify. Full simplify, I don't know how sophisticated it's, okay, so another one is, let's see, to what extent is fine distribution also a thing related to this? Is this some, okay, so we've got things like full simplify, how is fine distribution related to this? Because in fine distribution, you're essentially, I have to go to a different meeting in just a second here. This is a terrific topic, and we need to continue it. And I think we're going to get something. I mean, so we've got, our technologies here. Just to summarize, we've got multi-way system is one technology. We've got find equational proof is another technology. We've got, Z3/mini Canron. What other technologies do we have that are relevant to this?
There's data log, which is a lot more related to the kind of data set like transformations on top of data.
Okay, but what other, do we have other internal technology that is relevant to this? Maybe, although we don't really understand it, active classify.
In relation to groups, again, we have group element word, which decompose any group element into generators.
Okay.
And in relation to that, so these find path functions, should they return the list of states or the list of steps?
You got to be able to ask for both of them.
Okay.
Right. I think we got to be able to, the length, the endpoint, the steps. I mean, this is the notion of event specification. The things you apply are the events. The states you get to are the states. If you understand what I'm saying. And in the multi-way system case, we understand we need both of those. Right. And we have developed quite, and there's also things you might want, like the branch pairs. Right, that would be a useful thing to the result might need, all the things that we need in instrumenting multi-way systems are potentially useful here.
Right, but then you're in the world of computing MGUs and things.
No doubt, but the point, Jonathan, is this. My point is, how do we make something that's understandable and useful to people? And these things like find a path that's understandable. These things where you're, anyway, okay, I have to go, unfortunately. This is a terrific conversation and we need to continue it, but not today. So thanks all and see you later. And thank you to folks on the live stream here. Actually, wait, hold on a second. Let me just look very, very quickly at there's a question. Inverse kinematics, that's another interesting, yes, that's another use case here is that we should be looking at. Josephus problem, yeah, I remember that as an example of this, okay. Encode constraints, and Nick says, encode constraints in a, in something similar to geometric scene. Oh, that's interesting. That's another technology that's another technology we have here is the find instance / geometric scene world. And I'd love to continue this, but I really need to go deal with a much more, right. And this whole, this is a general category of constraint programming, which we should list here, although what we're doing is breaking that down. But for the next time, we should start talking about that. All right, thanks guys. Thanks to folks on the live stream.